All right, here we go. It's the next video, okay, picking up where we left off. This is number 16 right here. Let's move on to number 17. Once again, I wish that I had these printed out so I could write on them, but it is what it is, okay? Number 17, the graph of the function f shown above has horizontal tangents at x equals 2 and x equals 5. Let g be the function defined by g of x is equal to accumulation function, all right? So g of x right here. Integral from 0 to x of f of t with respect to t. And they want to know where that function g, that's the original, has a point of inflection. Point of inflection, well, surely there must be some sort of test, okay? And there is, all right? You could see that we want the second derivative test. So taking the derivative of an accumulation function should be a piece of cake for you at this point in time. Drop the x in, integral sign goes away, dt goes away. But remember, I don't want the first derivative test. I want the second derivative test. So I know that g double prime of x is really just f prime of x. So that's the line I want to draw, right? The g double prime line, which is really the f prime line. Are you telling me I want to draw the line for the derivative of the graph that I'm given? Because that's when we check slope, increasing and decreasing. And you can see we go from 0 to 6 here. This thing increases until you get to 2. Has a positive slope, f, so that's why f prime is positive. That's why they told you there was a horizontal tangent, x equals 2. Even though you could eye it out here, you could see it decreases from 2 to 5. And then we can see it increases from 5 to 6, okay? So we want to know where g has a point of inflection. Well, there's two of them where g double prime changes sign at x equals 2 and at x equals 5. And that would be c right there. Okay, so really not a difficult problem, not a lot of work involved. If you know about your tests, you know how to take the derivative of an accumulation function. Moving on to number 18. Number 18 over here is a problem that actually does bother some people, not the easiest thing in the world. In the xy plane, they give you the line x plus y equals k, where k is a constant. It's a constant, is tangent to this graph right here. What is the value of k? So I actually told you that the x plus y equals k is a tangent line. That bothers people, okay, because usually we write those in y equals mx plus b form. I could write that, y equals negative x plus k right there. That's y equals mx plus b. And then they give you the original function. They say is y equals x squared plus 3x plus 1. They want to know what the value of k is. And you might notice that k, that's our y-intercept, right? That's really our b. Okay, so as far as figuring out what b is equal to, well, I need to know what x is, and I need to know what y is equal to. And the problem is, we don't know what x is, we don't know what y is. Usually if they want the equation of the tangent line, they tell us what x is, and then, we get the slope of the tangent line, slope of the tangent line, take the derivative. We actually know the slope of the tangent line this time. They told us the tangent line was negative x plus k. The slope is negative 1. So when you take your derivative, usually we're used to plugging an x value in. I don't know what the x value is now. I know what the slope is, okay? So a little bit different, a little bit backward from what we're used to. But believe it or not, now you can actually solve for x. Okay, so I know that subtract 3 from both sides. So I know that negative 2 is actually equal to x. Why is that useful? Well, if I have y equals negative x plus k, and I want to solve for what k is equal to, now I know that x is equal to negative 2, but I need y. But we know how you get y, okay? You plug x back into the original, so that's going to be f of negative 2, which we know is really just negative 2 squared, which is going to be 4, plus 3 times negative 2, so minus 6 plus 1. So is that negative 2 plus 1, so negative 1. And now I can solve. Negative 1 is equal to 2 plus k. Subtract 2 from both sides. K equals negative 3, which is a right here. Problem that a lot of people struggle on, but it's really not too difficult to do, okay? You just got to think about it and kind of work out of order a little bit. But it might be a chalk it up as an L for certain people, just like number 19 might definitely be as a chalk it up as an L for someone. Number 19, if you try to look at the percentage of people who got this question right, they didn't grade this question on the 2008 AP exam because so many people got it wrong, okay? That happens from time to time, not too often. But horizontal asymptotes, remember horizontal asymptotes, that end behavior of a function, end behavior, that's the limit as x approaches infinity of the function, or the limit as x approaches negative infinity of the function. which a lot of times is no difference, right? Polynomial function, rational function, pardon me, polynomial 2, you know, no difference as x approaches positive infinity or negative infinity. But there is here, okay, the limit as x approaches positive infinity of 5 plus 2 to the x over 1 minus 2 to the x. You could do it a couple different ways. You can compare terms of highest degree. X is approaching infinity. Think of the term of highest degree up top. I mean, this term has degree 0, right? 5x is 0. This term has degree x, and x is approaching infinity. X is going to be like 20 billion. You're going to have 2 to the 20 billion power, which is a ridiculously big number. Oh, but then you're going to add 5. You're going to add 5. He's not going to make any difference, okay? He's a term of lesser degree, just like the one downstairs, term of lesser degree. You should know what happens to 2 to the x. As x approaches infinity, you can see that 2 to the x is getting infinitely big. You should be able to graph that right there easily. So these guys are approaching infinity. These guys are just constant, okay? So they're going to get dwarfed over here, so we could totally wipe them out and say this is the limit as x approaches infinity. We could ignore those terms of lesser degree of 2 to the x over negative 2 to the x. Now you could say the degrees are tied. We divide, there's a 1 in front of this, 2 to the x, and negative 1 in front of this. 1 divided by negative 1 is going to be negative 1. Or you could just cancel 2 to the x with 2 to the x. You get 1 divided by negative 1, which is negative 1 that way. So that's a horizontal asymptote at y equals negative 1. But believe it or not, when you now do the limit as x approaches negative infinity of 5 plus 2 to the x over 1 minus 2 to the x, you'll see that 2 to the x, as x approaches negative infinity, it's getting closer and closer to 0. These guys are approaching 0. Really, x is like, you know, negative 20 billion, right? 2 to the negative 20 billion power, that degree of negative 20 billion, that's less than this degree of 0. So these are the terms of lesser degree that we could ignore, and this becomes the limit as x approaches negative infinity of 5 over 1, which is just 5. Remember, the limit of a constant, always that constant. So there's also a horizontal asymptote at y equals, not negative 1, y equals 5 right here, which you could see was E as far as our multiple choice are concerned. Too many people on the AP exam either just got the limit as x approaches infinity or limit as x approaches negative infinity. They didn't know to consider both of those. That's why so many people got that problem wrong. So just be careful with something like that. Moving on to number 20. Number 20 over here, actually really easy problem. We'll scrunch it in over here. Let f be a function with the second derivative given by this right here. What are the points of inflection of the graph of f? So here's the second derivative of f. They want to know the points of inflection of the graph of f. That means f is our original. Points of inflection, surely there must be some sort of test. And there is the second derivative test. And they give you the second derivative. People are like, I got to take the derivative of this twice. No, okay, just set it equal to 0. It's polynomial, by the way. If you distribute this out, it's never non-existent. If you set it equal to 0, all right, you don't tee it up, you pi it up. You get x squared equals 0, x minus 3 equals 0, and x minus 6 equals 0. So x equals 0, x equals 3, x equals 6. Those answers are all there in part E, but look, just knowing the second derivative equals 0 is not enough to know that you have inflection points. Remember, you need that sign change. And I know the second derivative is polynomial, so the original is polynomial, so it's unbounded. Doesn't make a difference here. You need to see that sign change in the second derivative. Second derivative is great. I'd plug into this version right here because x squared is always positive. So you can just worry about plugging in here and here. Plug in a negative 1. Negative 1 minus 3 is negative 1, negative. Negative 1 minus 6 is negative. Negative times negative is a positive. Plug in a 1. 1 minus 3 is negative. 1 minus 6 is negative. Negative times negative is a positive again. Plug in a 4. 4 minus 3 is positive. 4 minus 6 is negative. Positive times a negative is a negative. And if you plug in like a 7 or a 3,608, you get a positive times a positive, which is going to be another positive. So it's actually only at 3 and 6 that the sign of the second derivative changes, okay? So that's why there are inflection points at 3 and 6, okay? Which I believe is part D right there. My kids are really being extra loud and crazy upstairs. Hopefully you don't realize that. Or listen to that or hear that. And you might be like, wow, these problems are really tough. AP review, Mr. Berto. Remember, if you want to get a 4, if you want to get a 3, pardon me, you really want to average 4 correct out of every 10 problems. You only need about 40% of the exam correct. Obviously, it's different for your exam this year, but they're still going to at least try to stick to that criteria right there. Might be a lot easier to get a 3 or 4 or 5 this year than any other year. Who knows? 21, a particle moves along a straight line. Is it horizontal? Maybe. Horizontal line motion. The graph of the particle's position right here at time t is shown above from 0 to 6. Horizontal tangents at t equals 1 and t equals 5. A point of inflection at t equals 2, which is kind of cool. They want to know the values of t for which the velocity of the particle is increasing. If you try to think about this just commonsensically, looking at a position graph, it's not easy to see when a velocity is increasing. I'd go to the math, okay? If velocity is increasing, that means the derivative velocity is going to be positive, right? And the derivative velocity is acceleration. So you want to know where acceleration is positive. So I actually want to, that's where I draw the line. The A line, okay, the V prime line, all right? So here the A line is going to be bounded from 0 to 6. Check this out. It is the A line. The A line is really the V prime line, but we have position. That's really the X double prime line. We don't really do this too often. We spoke about it once in class before, but if you want to draw the line for the graph that you're given, that's when you check above and below the t-axis. If you want to draw the line for the derivative of the graph that you're given, that's when you check increasing and decreasing, because the derivative tells you about slope, increasing and decreasing. When you want to draw the line for the second derivative of the graph that you're giving, that's when you check concavity, okay? A second derivative represents concavity. And here you can see that this function starts out by being concave up until right here at this inflection point at t equals 2. So it's concave up. X double prime is positive, which means acceleration is positive from 0 up to 2. And then you can see the rest of the way from 2 to 6, it looks like an N, which means it's concave down. Okay, and right there, if you want to know when the velocity of the particle is increasing, that's when acceleration is positive. That's from 0 to 2, which is multiple choice selection A. Not so easy, okay? Definitely a difficult problem. But once again, if you want to draw the line for the second derivative of the graph that you're given, that's when you check concavity. Not something that we do a whole heck of a lot. Moving on to number 22. 22 deals with something we dealt with last chapter. A rumor spreads among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard the rumor. If P denotes the number of people who have heard the rumor, which of the following differential equations could be used to model this situation with respect to time t, where K is a positive constant? If the rumor spreads among a population at a rate proportional to the product of the number of people who've heard the rumor and the number of people who've not heard the rumor, remember, a rate proportional, that means directly proportional. And if two quantities are directly proportional, that means you can multiply one by a constant to create the other. So here, the rumor spreads along among a population of n people at a rate proportional to the product and number of people who've heard the rumor and the number of people who have not heard the rumor. P denotes the number of people who have heard the rumor. So the rate of spread of the rumor, as time goes on, that's going to be the rate at which the number of people who heard the rumor, I need to maximize my instructional space right here, number 22. That means the rate at which the number of people who heard the rumor, it's dp over dt, right? The number of people who heard the rumor with respect to time. See, all these are dp over dt, is directly proportional, which means you can multiply by a constant to create dp over dt. What is it directly proportional to? The product, so there's going to be multiplication here of two things, of the number of people who have heard the rumor and the number of people who have not heard the rumor. P is the number of people who have heard the rumor. They don't tell you the number of people who have not heard the rumor, but if you take that total population of n and you subtract the number of people who have heard the rumor, you get the number of people who have not heard the rumor. Okay, and that's actually our answer right there. Kp times the quantity n minus p, that would be B. So remember, if two things are directly proportional, it means you can multiply one by a constant to create the other. They always multiply the constant by the amount. They never multiply it by the rate. Okay, so something to think about right there. Not the easiest problem, but it's one that we did speak about. Okay, a problem of that type. Moving on here now to number 23. Looks like more differential equation action here. Okay, for number 23. Okay, which of the following is the solution to this differential equation? dy over dx is equal to, we got x squared over y Then they give you that in Ishkandish, that y of 3 is -2. Okay, so look, if we want to solve this right here, hey, separate and integrate, okay? Cross multiply, always put the dy on the left-hand side. Y dy is equal to x squared dx. You're already separated. You don't need to move anything, so you could simply integrate. All right, integrate y to the first, we get y squared over 2 equal to integrate x squared. That's going to be x cubed over 3 plus c. Don't forget to add that plus c. This is a general solution. I usually don't solve for y until I solve for c, but I will clean up the left-hand side. Always try to keep the left-hand side as clean as possible. Multiply by 2 on both sides. I get y squared is equal to 2/3 x cubed plus c times 2, just another c, right? Just another constant. And that means now that's the general solution that I'm going to use, because if I want to solve for y, I'd have to take the square root of both sides. That's an advanced algebraic technique. I don't use an advanced algebraic technique until I solve for c. We know that when x is 3, y is -2. All right, so we could use that info to solve for c right there. This is going to give us, I'll put it over here, that what, 4 is equal to 3 cubed is 27, divided by 3 is 9. 2 times 9 is going to be 18 plus c. Okay, subtract on both sides, and I get that -14 is equal to c. And make sure you plug that into the general solution that you use to generate that particular value of c. So now I know y squared is equal to, I'll write this as 2x cubed over 3, because that's the way they do it in the solutions, -14. And now you should know it's either D or E right here. Some people pick C. Those are the people who don't bother to actually put the plus C when they integrate. So be careful with something like that, okay? Anyway, I just have to worry about positive square root and negative square root. You know, we're taking a square root here. And remember, it's going to be a positive square root if the y value you get back is positive, and a negative square root if the y value you get back is negative. You could see that y is negative here, less than 0, which is why the square root has to be negative. You know, you could try, leave it as a positive square root. If you plug in the 3, you'll get back a positive 2. We want a -2, okay? So that's why my answer is going to be E right here. So not the easiest differential equation, because a lot of people might do all that work and then put D, not taking the correct square root, and what a waste of time that is. So be careful. You know, 24, really cool abstract derivative problem right here, abstract information. They tell you the function f is twice differentiable, which means it's nice. You could take 2 derivatives. They tell you f of 2 is 1, f prime of 2 is 4, f double prime of 2 is 3. What is the value of the approximation of f of 1.9 using the line tangent to the graph of f at x equals 2? An approximation of f of 1.9 using this tangent line at x equals 2, local linearity. Don't give me no disparity. If you want to approximate a function at a nasty x value, create a tangent line at a friendly x value close by and plug the nasty x value into the tangent line. Here they tell you where to create the tangent line. Some people are like, I'd rather just plug 1.9 to the function. It's not really a nasty x value. Well, good luck. They don't even tell you what the function is. But if you want to get the tangent line at x equals 2, well, first you need the slope of the tangent line. Slope of the tangent line. Take the derivative and plug in. People are like, well, I don't even know what f is. How do I get f prime? And then how do I get f prime of 2? Well, they told you what f prime of 2 is, right? They told you it's equal to 4. It's the slope y'all are looking for. Second, let's plug in y equals mx plus b. Replace everything but the b. Ow! Stung me. We know that m is 4. We know that x is going to be 2. And then to get what, this is a 4, not a y. To get what y is equal to, we plug into the original. And remember, it's the line tangent to f, so we want f of 2. People are like, I don't have f. How am I going to know what f of 2 is? It's right there. They told you what it is, Poppy. All right, so 1 is equal to 8 plus b. Subtract 8 from both sides. -7 equals b. Therefore, even though there are 3 dots, y equals 4x minus 7. Look, that's what I want to plug into as far as, you know, approximating. As long as you're really close to x equals 2. You don't know what f is, but we know this gives you a good approximation of f close to x equals 2. So f of 1.9, really 4 times 1.9 minus 7. 4 times 2 would be what? 8, but it's 4 times 1.9. So that's going to be 0.4 less than 8. So 7.6 minus 7 gives us that desired result of 0.6, which is there in part B. So a little local linearity problem right there for number 24. Some people realize, hey, why do they tell you f prime of 2 is equal to 3? They don't often give you extra information that you don't need. Here you don't need it. But I have a theory about this question. I think that originally they were going to ask you something else here. You know, now that you know that f double prime of 2 is equal to 3, sometimes they ask you this. Sometimes when you get the approximation, I don't know what f looks like, but I know that at x equals 2, f is equal to 1. So I know the point 2 comma 1 lies on the graph of the function f. Okay, and what do I know about x equals 2? I know at x equals 2 now, if f double prime of 2 is equal to 3, f double prime of 2 is equal to 3, 3 is positive. So if a second derivative is positive, it means the function's concave up. So at x equals 3, I know this function's going to be concave up. It's going to look like a U. I don't know exactly how it looks, but maybe a little something like that. Doesn't need to be a minimum here. That's not what I'm meaning to draw right here. I'm just trying to say the function's going to be concave up. Let's make it do a little something like that right there. So the minimum be a little bit to the right. Here, sometimes they ask you if your approximation is an under approximation or an over approximation. Something we'll talk about more when we get to AP review. But here's the tangent line, okay, to the graph of the function f at x equals 2. And think about that 1.9 that we're plugging in. That 1.9 is going to be right here. Okay, obviously it's a lot closer. But if you plug 1.9 into f, you get this value right here. Okay, that's f of 1.9. We plug 1.9 into the tangent line, which means we got back this y value right here. That's the approximation of f of 1.9. Look, they should be even closer than that, okay? Because this point is going to be even closer to this, okay? Because you can see, plugging into the tangent line, plugging into the function, it's almost like you're plugging into the exact same thing. But check this out. Because the function is concave up, you could see that what we got right here was we actually got an under approximation. So our approximation right here, this is an under approximation. And that's because f was concave up, conc up. You'll see that anytime a function is concave up, when you try to do the tangent line approximation, your answer, no matter where the tangent line is, will always lie below the curve, okay? So believe it or not, when a function f is concave up, then local linearity, the tangent line approximation, will always under approximate, which is something they're going to ask about later on, you know, when we do AP review. It's not something that shows up every year. It just happens really every now and then. If f is concave down and you actually plug in to a tangent line, you'll see the tangent line is always going to be above the function, no matter where you write it, okay? So if f is conc down, then local linearity will actually always over approximate. Will always over approximate. Okay, and they might, you know, here I think originally maybe they want to know if the answer was an under approximation or an over approximation. It's really an under approximation because f is concave up. The real reason is because f double prime of 2 is positive. That means that f is concave up. We'll talk about that more and more. Okay, you could obviously solve the problem without thinking about any of that, but something to think about in the future because it's something we're going to see on the AP. Maybe you'll see it on the AP, maybe you won't. Moving on to 25. Classic problem right here, okay, just a little bit annoying, okay. Let f be this function defined above. C and d are constants. They're constants. They tell you f is differentiable at x equals 2, which is luscious, right? Because if it's differentiable, that also means it's continuous, okay? And you want to know what the value of c plus d is equal to. Well, if the function is continuous, the limit exists. So since the function is continuous, we'll focus on x equals 2, because that's the trouble spot right here. That means the limit as x approaches 2 from the left-hand side of f of x equal to limit as x approaches 2 from the right-hand side of f of x. Remember, that's not the only thing with continuity. That means the limit right there is also going to be equal to f of 2, but I know if a function is continuous, I know the limit's going to exist. So this right here, if you approach 2 from the left-hand side. Let me fold this paper. Make it easier to show you what I'm trying to show you over here. Okay, if you approach 2 from the left-hand side, you can see you're plugging into top dude. So x is equal to 2, so c times 2 plus d. And if you approach 2 from the right-hand side, you're plugging into bottom dude. So 2 squared minus c times 2. So that gives us 2c plus d is equal to 4 minus 2c. And here, this is an equation in 2 unknowns, okay? You could add 2c to both sides if you want to and end up with 4c plus d is equal to 4. But the problem is I'm not going to be able to solve that until I get another equation. And the other equation, we're going to use the fact that this function is differentiable. And that means that you could take the derivative f prime of x equals 2. Remember how to take the derivative of a split function? Take the derivative of the top and bottom. Little abstract derivative, right? The derivative of cx plus d. C and d are constants. That's a linear. The slope is c. Derivative is just c. It's like the derivative of 3x plus 2 would be equal to 3. The derivative of cx plus d is equal to c. Normally, we don't include that trouble spot right away. We got to check for differentiability, but they told me it was differentiable. Bottom dude's slope is going to be what? 2x minus c. And now we can actually set up that check for differentiability. And that's really not, is the function approaching the same y value from the left and from the right. That's, is the function approaching the same slope from the left and from the right. And we know this has to be true. Search your feelings, you know it to be true. So we'll do the limit of f prime of x right here. We know f prime of x, if you approach 2 from the left, you plug into top dude, you just get c. Doesn't matter what you plug into top dude. If you approach 2 from the right, you plug into bottom dude, 2 times 2 minus c, which means c equals 4 minus c. Now you got another equation. Add c to both sides, 2c equals 4, which means c equals 2. And if c equals 2, we know that when you plug that in here, we get 4 times 2 plus d is equal to 4. So that's 8 plus d equals 4. Subtract 8 from both sides. D equals negative 4. What they want to know, by the way, c plus d. And c plus d is going to be 2 plus negative 4, which gives us an answer of negative 2, which I could see there is B, okay? So a problem that we actually did before earlier in the year, a lot of stuff to write out, but a problem that's doable, but not easy. I believe if you look at the, the answer key, you'll see that not a lot of people actually got that problem right on the AP exam, which is the way it works for a lot of problems on the AP exam. Number 26. What's the slope of the line tangent? Slope of the tangent line. Take the derivative to the curve. Y equals arctan 4x. Okay, at x equals 1/4. You got to know how to take the derivative of arctangent, okay? Remember, that's really tangent inverse. Don't forget the derivative with respect to x of tan inverse u is going to be 1 over 1 plus u squared times du over dx. We talked about that before school was suspended. Also, the derivative with respect to x of sine inverse u works off a tangent 1 over the square root of 1 minus u squared times du over dx. Really just need them memorized here, and you can't even see what I'm writing. It's right here. You really just need them memorized. So now dy over dx. We know that u is really my 4x right here. Okay, and look, this is tan inverse of u, okay? So I know it's 1 over 1 plus u squared, which is 4x quantity squared. Don't forget, chain rule, you should know that. You're taking the derivative of a function whose argument is not one single x, multiplied by the derivative of that argument later on, and we get 4 over 1 plus, what, 16x squared? Which if you take a look, oh, sorry, we want to evaluate this, okay? So evaluate it when x equals 1/4. All right, so that's really going to be 4 over 1 plus 16 times 1/4 squared. So 16 times 1/4 squared, 1/4 squared is 1/16. 16 times 1/16 is going to be 1. So 4 over the quantity 1 plus 1 is really 4 over 2, which gives us our answer of 2 right there, okay, which is multiple choice selection A. It's actually a lot easier if you plug the 1/4 in right here. 4 times a fourth is going to be 1. Square that 1, you get a 1. 1 plus 1 is 2, and 4 divided by 2 gives you 2 that way. So other ways to do it. I think we're finally up to the last problem here. No, there's 27 and 28. Oh, but we're almost there. A little slope field action. Okay, so shown above is a slope field for each of the following differential equations. We just talked about stuff like this. You can go dependency if you want to. You could see if you move in a horizontal line, the slopes change, so they are dependent upon x. If you move in a vertical line, the slopes also change, okay? So that means that they're dependent upon y as well. So, you know, 27 dependent on x and y, which is actually great, because if you look at the multiple choice solutions, you can wipe out E right there. Hee, wipe out. Wipe out, right? Bow. Bow. All right, I'll stop that. Anyway, you could wipe out E. And then, by the way, if you're strapped for time, you could just guess one of them. If you could eliminate one answer, you put yourself in a great guessing situation. Your AP would only have 4 multiple choice solutions, but not your AP, because there's only going to be 2 free response questions. But anyway, maybe think about the slope of 0. You could see that when y equals 0, we have a slope of 0 here. Slope of 0 when y equals 0. That works here in part A. Part B, if y is 0, you get a slope of 0. Part C, if y is 0, you get a slope of 0. But in part D, if y is equal to 0, you get a slope of whatever the x-coordinate happens to be, which is not true over here. The x-coordinate's not always 0. So you could wipe out D and E. D and E. And then we have another slope of 0 when x equals -1. Do you see that? So you also know that slope equals 0 when x equals -1. Here, if you have part A, if x is -1, it doesn't guarantee the slope is 0 here. So really, we've narrowed it down to B, which is dy over dx, which is xy minus y, and then dy over dx for C right here, which is xy plus y. You can just plug in a point at this point if you want to. I mean, you know, plug in maybe what this point would be 2, 2. You're supposed to get a positive back. You could plug in you know, -3, positive 2, and you're supposed to get a negative slope back. Really, the easiest way to do it is to factor here. And if you do factor out of y, you'll see that now both of these, when y is 0, you get a slope of 0. But here, when x is -1, here, -1 minus 1 is a -2. Doesn't necessarily guarantee a slope of 0. Here, -1 plus 1 is 0, would guarantee a slope of 0, which is why C is actually our answer right there. Not the easiest slope field, but probably not the most difficult. Finally, number 28 right here is the end of this part A. Okay, 28. 20's not hungry because he had dinner. Let f be a differentiable function such that f of 3 is 15, f of 6 is 3, f prime of 3 is -8, f prime of 6 is equal to -2. When will this end? The function g is differentiable. Oh, and g of x equals f inverse of x. So g is the inverse of x, and they want to know what g prime of 3 is. Oh, they want the derivative of the inverse. And if you look at the solutions for this right here, I'll take a quick gander. All right, if I look down at my solutions, I could see in number 28, 14%. 14% of the people who took the AP exam in 2008 got this right. Most people get these problems wrong. You'll get it right, hopefully. Will it show up in one of your free response questions? I don't know, okay? I don't know if they're going to make one free response, just like a bunch of multiple choice questions or fill-in questions. Anyway, to do derivative of the inverse, it's not too difficult. Set up the g of f of x equals x, okay? Inverses cancel each other out. Always put the inverse on the outside. So if f was the inverse, I'd do f of g of x equals x. Take the derivative of both sides. G prime of f of x times f prime of x, little abstract chain rule practice right there. Take the derivative of the outside function, rewrite the inside function, multiply by the derivative of the inside function, equals the derivative of x, which is 1. And now solve for g prime of f of x, and that's 1 over f prime of x. Remember, I want g prime of 3. So I want f of x to equal 3. People are like, what the heck does x have to equal if f of x equals 3? Take a look, it's right here. X has to be equal to 6. It's very simple here, okay? And that means replace the x with a 6. Bothers some people. They're like, well, I didn't want g prime of f of 6. I wanted g prime of 3. But f of 6 is equal to 3. So really, g prime of 3 is equal to, oh, well, what's f prime of 6? Because they didn't even tell me f. How am I supposed to know what f prime of 6 is? It's right here. It's -2. Probably one of the easier derivative of the inverse problems. And that answer is -1/2, which is just A right there. But as I told you, 14% of the people who took the advanced placement exam in 2008, just checking that number again. Yep, 14% got that problem correct. You could be one of the 14%. Anyway, so that's the end of part A. No calculator there. I'm probably going to break that up over a certain amount of days. I'm thinking right now that'll be your assignment for Wednesday, Thursday, probably Friday as well. And then Monday, we'll talk about the actual part without the graphing calculator, a little bit shorter here. And then probably Tuesday of next week, we'll start getting into topic-specific review. Okay, we'll see how that goes. Do the best you can. Try not to be overwhelmed. Join my remind. Okay, you're going to be getting take-home assignments throughout the fourth quarter. And keep working, folks. Okay, I know that you're distracted right now. Life will go on, okay? And you will be in college. You'll need to know these concepts, so you'll want that AP score to be high. We went through so much this year and last year. Let's keep rocking and rolling, folks. Love all you guys. Hope that you're safe and healthy and happy. And we'll talk to you next week. Adios.